At the very heart of the Standard Model, our best theory of reality, there's a problem, a kind of glitch in the system. It's a puzzle of impossible perfection, and it challenges pretty much everything we think we know about the universe. Today, we're diving deep into a cosmic mystery, the strong CP problem.
And this whole mystery, it really kicks off with a simple question about a particle we've all heard of, the neutron. See, according to our theories, the neutron should be just a little bit lopsided. Its positive and negative charges shouldn't be perfectly centered, but every time we look, it's perfectly, almost impossibly, symmetrical. The question is, why?
Now, trying to find an answer here has basically split physicists into two camps. One path points to this ghost-like particle that might have been hiding from us for decades. But the other path, it suggests something way more profound, that the answer isn't a particle at all, but is actually woven into the very fabric of spacetime.
Okay, so before we can really dig into these wild solutions, we've got to get a handle on the problem itself, this incredible cosmic balancing act. So if we want to get technical for a second, the problem comes from quantum chromodynamics. That's our theory for the strong force, the stuff that holds atomic nuclei together. The math for this theory includes a certain parameter, a number that should create that little imbalance in the neutron. But for some reason we just can't explain, experiments show that number is, well, it's basically zero.
All right, think of it this way. Imagine the neutron is like a spinning top. The laws of physics, as we understand them, say it should have a definite wobble, what scientists call an electric dipole moment. But when we actually go and measure it, we find it spinning perfectly upright. No wobble at all. It's a balancing act so precise it just feels wrong, unnatural even.
Just how perfect are we talking about here? Well, the value of this parameter is less than 1 part in 10 billion. There's absolutely nothing in the Standard Model that says it has to be this small. It's like trying to throw a dart from Earth and hitting a bullseye the size of an atom on Pluto. That level of fine-tuning just screams for an explanation.
So, for decades, the number one suspect in this whole mystery has been a hypothetical new particle. So, let's meet the axion.
Back in 1977, a couple of physicists, Peccei and Quinn, had this really elegant idea. They thought, hey, what if we don't have to just force this number to be zero by hand? What if there's a natural mechanism in the universe that does it for us? And their theory predicted that this mechanism would create a brand new particle, the incredibly light and incredibly elusive axion. So how is it supposed to work? Well, the theory proposes a brand new symmetry in the universe. Then, in the crazy hot moments right after the Big Bang, this symmetry breaks. And when it breaks, bam! This new particle, the axion, just pops into existence. And here's the crucial part. The axion field then naturally settles down, and in the process, it automatically cancels out that troublesome parameter, solving the whole problem. It's a beautiful, self-correcting fix.
For the longest time, the axion looked like the perfect culprit. Case closed, right? Well, not so fast. Because like in any good mystery, there's a twist. And it turns out this perfect solution, it might have a fatal flaw.
And this is the question that's really bugging physicists now. The whole axion balancing act is, well, it's incredibly delicate. So what if the universe, in all its chaotic glory, especially when you start mixing in the effects of gravity, is just too rough for this fragile little fix to actually work?
And that brings us to what's called the axion quality problem. See, for the axion to do its job, the symmetry that creates it has to be almost perfect. But we have a pretty strong suspicion that at the highest, most insane energies, the churning quantum foam of spacetime, where things like microscopic wormholes might be flickering in and out of existence, would just shatter that symmetry. Even a tiny break spoils the whole thing, and our original problem comes roaring back. Suddenly, our prime suspect's alibi has a huge crack in it.
Okay, so if our prime suspect's alibi is falling apart, we need a whole new theory, right? And this one's a game changer. It suggests the solution isn't a particle at all. It's something way, way bigger.
So what if we've been looking in completely the wrong place this whole time? What if we don't need to invent some new particle to solve the puzzle? What if the solution has been hiding in plain sight all along, baked right into the structure and the geometry of our universe? There's this new idea on the block. It's called the Nexus Paradigm, and it proposes exactly that. It pictures spacetime not as just this boring, passive stage where physics happens, but as an active player in the game. In this idea, spacetime itself can have these little ripples in its geometry that actually respond to that imbalance from the strong force and just absorb it.
Kind of like if you put a dent in a rubber sheet, and the sheet itself just naturally smooths it out. No extra particle needed. So you see, we've got two completely different ways of thinking about this. The axion solution, it's all about adding a new character to the story, a new particle that fixes things. But the geometric solution, it says we just need to understand the stage itself, space-time, in a totally new way. It's a huge shift from a particle fix to a structural one. All right, so here we are, two powerful, totally different theories, a ghost particle versus the fabric of reality itself. So how on earth do we figure out who's right? Well, the answer lies in what they predict we should see out there in the cosmos.
Let's just lay it all out head to head. You've got the axion, a new particle, but it's really fragile and might not survive the chaos of quantum gravity. Then you have the geometric solution. It uses space-time itself, so it's naturally tough and protected. But here's the most important part. They tell us to look for completely different kinds of clues. One says we should find a particle in a lab. The other points to subtle, weird effects in gravity across the entire universe.
Right. So if the axion is real, we got to be able to find it. And all over the world, scientists are on the hunt. You've got experiments called haloscopes like ADMX that are basically giant, super cold chambers listening for the faint whisper of an axion turning into a photon. Then there are helioscopes like IXO that are staring right at the sun, hoping to catch axions being born in its fiery core. We are actively looking for this ghost.
But, and this is a big but, if the geometric idea is right, all those particle detectors will come up empty. Instead, we need to be looking for these weird, subtle asymmetries in gravity, things that aren't perfect mirror images. This could be a tiny rotation in the polarization of ancient light left over from the Big Bang, or maybe a slight difference between left and right-handed gravitational waves. Even the Event Horizon telescope could potentially spot strange polarization patterns right at the edge of a black hole, betraying this deep link between spacetime and this strong force.
And this really leads to a pretty profound idea, captured perfectly in this quote. The Nexus Paradigm reframes the strong CP problem not as an isolated fine-tuning issue, but as a deeper manifestation of quantum space-time structure. So what does that mean? It means this whole problem isn't some random bug in our theory. It's a feature. It's a giant clue telling us about the deep quantum nature of space-time itself, linking the very, very small with the very, very large.
So that's where we are, on the edge of this incredible cliffhanger. Is the solution to physics' most perfect problem a tiny new particle just waiting for us to find it in a lab? Or have we been living inside the solution this entire time, with the answer written into the very geometry of our reality? The hunt is on. And honestly, no matter what we find, it's going to completely change how we see the universe.